Hi, good morning all. A warm welcome to this second day of Tecnicelpa discussions. This session is dedicated to energy, environment and sustainability. And we were the ones selected to test the stage after the tuna, because with so many jumps, there was some safety issues during the night. And now we are trying to check if everything is okay. First of all, we have to excuse Katia, the first presenter. She couldn't make it here because unfortunately she got ill. So we'll be short on one presentation, but still we have a very good discussions and teams to start this morning. And to start off, we'll start with the presentation entitled Wastewater Treatment Plant Optimization by Catarina Rebelo. Catarina Rebelo, I'm a bit suspicious because I'm his chief, but she's a chemicals master's from Aveiro University. She joined RAIZ in 2015 and have been working there in several areas from wood characterization, wood consumption, wood technology, and in the last few years, she dedicated a long time to wastewater treatment plant optimization. And she will share with us her experience on this theme. Thank you all. Catarina, please.
Good morning, everybody, and welcome. The slides are in English, but my presentation will be in Portuguese, but feel free to ask any questions in English or Portuguese. Esta apresentação vai dividir-se em 4 partes: a introdução, a metodologia, os resultados deste projeto e também as conclusões. Penso que a maioria das pessoas aqui presentes teve que lidar com a pressão nos recursos hídricos no seu dia-a-dia no trabalho. A escassez destes recursos levou a uma maior consciencialização da sociedade e também levou a uma implementação de requisitos legais mais restritivos para a gestão da água. O que na prática se traduz em valores de emissão mais restritivos para o efluente descarregado, mas também um maior controlo na sua monitorização. Para fazer face a esta nova realidade, as fábricas têm que se adaptar rapidamente para garantir a qualidade do efluente descarregado de forma a cumprir estes novos requisitos legais. A metodologia, a estratégia seguida neste trabalho foi desenvolver um programa de testes onde variáveis como a idade das lamas e o doseamento de nutrientes foram otimizados para mantendo todos os outros parâmetros constantes ou sob controle ou vigilância. A metodologia seguida foi uma metodologia passo a passo. Começamos por uma auditoria inicial à instalação para perceber quais as oportunidades de melhoria, o que é que se poderia identificar e melhorar. De seguida, todas essas sugestões de melhoria verteram-se para um plano de trabalhos que foi implementado nas fábricas, o que foi possível. Durante esta fase do trabalho, verificámos que muitas das vezes seria necessário conhecer as correntes parciais que chegam à etar, porque muitas vezes as fábricas o que fazem é uma monitorização do que é pedido nas licenças, portanto é muito mais virado para o que é descarregado e é isso que se é mais monitorizado. E então, nesta fase, fizemos um survey de efluentes para conhecer melhor as correntes parciais e perceber quais contribuem mais ou menos e qual o seu impacto na etar. Na última fase, e a mais importante, seria então a otimização das condições processuais que iríamos no final do trabalho definir para que a etar ficasse otimizada. De todo este trabalho, então, começando pela fase da auditoria, numa pré-fase da auditoria construímos este Excel, uma ferramenta Excel com toda a informação relevante da etar para que tivéssemos toda a informação em preparação para a auditoria. mas depois veio-se a revelar, posteriormente, uma ferramenta bastante importante para a ajuda à decisão no dia-a-dia da operação da ETAR por parte da equipa de ambiente e da produção. O relatório, em conjunto com a equipa da AFRI, onde espelhou a situação atual da instalação, no momento da auditoria, que depois de analisada, passamos então para um plano de ações, onde se identificaram os impactos, o que tínhamos que melhorar e as pessoas responsáveis pela sua implementação. De seguida, passamos então ao survey de efluentes, onde, para perceber melhor então o que chega à ETAR das correntes parciais, definiram-se os pontos de amostragem, recolheram-se amostras, caracterizaram-se o laboratório e, com balanços e todas estas caracterizações, percebemos quais têm mais impacto ou menos impacto no que chega à ETAR. E conseguimos quantificar esses impactos. De seguida, a parte principal, os resultados deste trabalho, onde se obteve informação crucial para perceber quais as condições que iríamos definir para otimizar a ETAR. Nesta fase também foi muito interessante porque, apesar de conseguirmos esse objetivo, que era ter dados suficientes para depois analisar e otimizar a ETAR, muitas das vezes, como estamos a fazer um acompanhamento muito próximo e detalhado, conseguimos verificar o que é que acontecia à ETAR quando havia variabilidade processual, quando havia perturbações no processo, que é normal em todas as fábricas isso acontecer, e que não é possível no dia-a-dia de estar com esse detalhe e com essa atenção. Por fim, as ferramentas que resultaram deste trabalho foi mais uma vez o Excel, que tem toda a informação e está a informação de uma forma muito user-friendly e que nos permite a todos os dias atualizar e verificar se temos que fazer alguma mudança na ETAR ou se existe algum problema. Tínhamos reuniões todos os dias com a equipa para perceber o que é que se estava a passar e se tínhamos que fazer algum ajuste. Grupos de WhatsApp, hoje em dia, não é? Toda a gente tem não sei quantos grupos de WhatsApp para comunicarmos com todos e para, se houvesse algum problema, de imediato conseguimos ter uma resposta. E, no fim, mas não menos importante, um documento bastante importante que em todos os projetos de otimização das ETARs, no fim, temos um documento, não só o relatório do projeto, mas também um documento que vai compilar toda a informação das lições aprendidas durante o trabalho e que servirá como uma boa base para o futuro de troubleshooting. Então, durante a fase de otimização das condições processuais, fixámos algumas variáveis ou condições, como a idade das lamas a 20 a 22 dias, a média móvel a 7 dias, o oxigênio dissolvido nos tanques de arejamento, o pH, a temperatura à entrada do tratamento biológico. Cada fábrica, penso que deva ter estas condições definidas, para quais são valores definidos de condutividade ou de pH, para se poder desviar o efluente para a bacia de emergência, caso haja alguma perturbação, e depois dosear ao tratamento biológico para ter menos impacto. E, caso seja essa a realidade da instalação, se já adiciona um auxiliar de sedimentabilidade, manter essa dose para haver menos entropia durante o estudo. A variável manipulada acaba por ser a razão, ainda que indiretamente, a razão azoto CQO, à entrada do tratamento biológico, indireta porque o que nós manipulamos é a dose de nutriente, no nosso caso a ureia, que variamos esta dosagem para obter 3 condições de razão azoto CQO, uma mais baixa, uma média e uma elevada, e mantínhamos esta condição cerca de 15 dias para termos informação suficiente e representativa para o estudo. Depois, convém manter sempre debaixo do olho os MLSS nos tanques de arejamento, os sólidos suspensos totais à entrada do biológico, a sedimentabilidade através do famoso XVI e a observação microbiológica. Tudo isto para termos os parâmetros de performance otimizados, como a garantia do cumprimento legal do efluente descarregado, que é o mais importante, a sedimentabilidade, que irá também contribuir para isso, e a biodegradabilidade. Passamos então aos resultados e discussão, começando pela sedimentabilidade. Neste gráfico temos representado a variação dos sólidos no efluente final com a idade das lamas. O que fomos fazendo foi aumentar, porque normalmente as fábricas tinham a idade das lamas mais baixas, foi aumentar a idade das lamas para ver o que acontecia. e para depois podermos fixar no que achávamos ser ideal, e pode-se verificar que, à medida que fomos aumentando a idade das lamas, os sólidos foram diminuindo e estabilizando num valor mais baixo. Em relação à razão azoto-CQO, ao aumentar esta razão, como se pode ver neste primeiro, não consigo apontar, mas é neste primeiro gráfico, verificamos que, à medida que vamos aumentando a razão azoto-CQO, gradualmente, os sólidos no efluente final também vão descendo e mostram uma boa correlação. Até que, ali a partir dos 1,5, mantemos os valores de sólidos muito baixos e constantes, o que é o que toda a gente pretende. Em relação ao SVI, também podemos verificar que esta redução gradual, este aumento gradual da razão azoto-CQO impacta na sedimentabilidade, visto que o SVI também vai descendo à medida que se vai aumentando a razão azoto-CQO, o que nos mostra que houve melhoria na sedimentabilidade das lamas. Este slide acho que é bastante importante, tem muita informação, mas eu vou tentar orientar. É um slide onde podemos ver a relação entre a razão azoto-CQO, o SVI e a idade das lamas. Isto trata-se de uma fatia de cerca de 2 meses de um trabalho numa das hectares. Pode-se verificar que, da fotografia 1 à 4, estamos numa fase inicial onde temos uma razão azoto-CQO muito baixa, em torno de 1 e às vezes até de 0,5, e uma idade das lamas acima dos 22 dias. Podemos verificar é que o SVI anda aqui em torno dos 200, o que é um valor bastante elevado e que demonstra fraca sedimentabilidade, que se pode verificar pelas fotografias do CONIMOF, em que temos um grande volume de lamas e praticamente nada de clarificado. A partir do momento em que começamos a aumentar a razão azoto-CQO, a partir da fotografia 5, e estabilizando a idade das lamas, nos 20 a 22 dias, verificamos que o SVI desceu drasticamente, estabilizando-se aqui num patamar por volta dos 100. Nos cones IMOV também se verifica, ao longo do tempo, que a sedimentabilidade melhorou bastante, aumentando a porção de clarificado em detrimento de lamas. Em relação à produção específica de lamas, como podemos verificar, ao aumentarmos a idade das lamas, também diminuímos a produção específica de lamas, o que é benéfico para termos menos lamas e resíduos para tratar. Ao aumentar a razão azoto-CQO, aumentamos a disponibilidade de nutriente, então vai haver muito mais produção de lamas, portanto é interessante ter aqui um compromisso entre uma idade que não seja também muito avançada, porque aí o metabolismo também decresce e não conseguimos ter uma remoção, uma biodegradação que pretendemos, apesar de termos uma produção específica baixa, que é o que interessa a nível de custos e de gestão de resíduos, mas também temos que ter aqui uma boa razão azoto-CQO para que elas cresçam e haja a remoção que pretendemos. Portanto, mais uma vez, é a combinação entre a idade das lamas e a razão azoto-CQO que nos dá aqui os melhores resultados, combinando aqui entre os 1,5 da razão da azoto-CQO a 2 e os 20,22 de idade das lamas. De seguida, temos a biodegradabilidade. Estas novas condições de operação levaram a um aumento da estabilidade operacional. Neste primeiro gráfico, o que podemos ver é uma linha do tempo da eficiência de remoção do CQO. Como podem ver no início, do lado esquerdo, temos uma grande expressão de valores e chegamos a atingir valores mesmo muito baixos, de 50, 55, 60% de remoção de CQO. A partir do momento em que começamos aqui a estabilização e depois que levamos o estudo até ao fim, conseguimos, a partir de uma certa altura, depois de tudo otimizado, estabilizar o valor de remoção de CQO em valores mais elevados e sem muita dispersão. Além de esta razão da azoto-CQO estabilizar esta eficiência de remoção de CQO, também promove a biodegradação, como podemos ver neste gráfico abaixo, em que temos a variação da razão azoto-CQO com o CBO5 no efluente final, e podemos ver que elimina praticamente todo o CBO presente no efluente final. Portanto, depois de todas as condições estudadas, definirmos as condições que são ideais para a nossa instalação, podemos verificar que os sólidos, que são as bolinhas azul aqui na base do gráfico, no efluente final, estão bastante estáveis e com pouca dispersão, e o próximo passo lógico seria, como toda a gente quer, de diminuir custos. Como? Adicionamos, no nosso caso, nas nossas fábricas, adicionamos argila como auxiliar de sedimentação, então por que não reduzir já que está tão estável e ver o que acontece? E percebemos que, à medida que fomos diminuindo gradualmente a dose de argila, não houve qualquer impacto na estabilização e nos valores de sólidos do efluente final. Portanto, a conclusão a tirar é que podíamos, tendo uma hectare otimizada, conseguimos remover a adição e o consumo de alguns químicos. Neste slide, é apenas alguns exemplos visuais do impacto no controle imediato da operação. Do lado esquerdo temos a observação microbiológica que, antes desta otimização e de todo este trabalho, que dura alguns meses, tivemos vários episódios e graves episódios de filamentosas. Como podem ver, praticamente não temos floco. Depois da otimização e desta fase de estabilização, já tínhamos uma lama muito mais saudável, praticamente não tínhamos filamentosas, apesar que elas podem estar presentes em pouca quantidade, sem haver problema, mas neste caso até não tínhamos nenhuma. Estão bem agrupados e flocos de boa dimensão. Do lado direito temos o famoso cone-move, que é algo que é fácil e rápido de fazer, acho que a maioria deve fazer nas suas hectares, por parte da operação, e que nos permite logo ter uma ideia em minutos de como está a qualidade da lama e do sistema, porque dá-nos logo uma ideia se a sedimentabilidade está boa ou não, e daí podemos tomar ações ou investigar o que é que se estará a passar. Conclusões. De uma forma geral, a metodologia desenvolvida pelo RAIZ, implementada nas fábricas da Navigator Company, foi bem sucedida na otimização da performance da hectare, de forma a garantir que cumpre os novos requisitos legais, mas também conseguir tornar a hectare mais robusta a variações processuais, a variabilidade processual, mas também alguma perturbação que possa ocorrer no processo. Deste trabalho, os principais outputs foram então a definição das condições ótimas de operação, de forma a garantir o cumprimento legal dos novos requisitos das licenças. Conseguimos aumentar a robustez da hectare perante distúrbios, perturbações no processo e alguma instabilidade. Reduzimos algum consumo de químicos e ficámos com boas ferramentas de suporte para a operação e também para troubleshooting. Obrigada.
Thank you very much, Catarina. Now the questions will be after the second presentation, Catarina, so you can join us here in the... And as Monty Python would say, now for something completely different. We have another presentation also in this environmental and sustainability area is getting very broad in terms of scope. And we now go from the final effluent treatment to product characteristics. And we have this presentation called Brown is the New Green, Eye Charts Pulp for Tissue by Cláudia Esteves. A few words about Cláudia. Cláudia is a chemical engineer from Portugal, finished her PhD at the Royal Institute of Technology in Stockholm last year, and she moved to Sweden in 2019 and been working in this research institute, RAIZ, not RAIZ, RAIZ, R-I-S-E, where she has been mainly working with oxygen lignification process, chemical pulping and paper characterization, including tissue paper. So let's hear Cláudia. Thank you very much.
Thank you very much. First of all, I'm sorry, my throat is a little sore, so I hope I don't need to interrupt the presentation. So, as Luís mentioned very well, my name is Cláudia and I'm Portuguese but I've been working in RAIZ, that stands for Research Institutes of Sweden, for almost 5 years now. And we are present in a lot of different cities and countries, and we have different fields of areas. But the one that I'm in is in the pulp, paper and packaging department, located in Stockholm. And you might not know RAIZ now because it's quite new, but it was the old Invencia or STFI that was well known in this field. And today I will talk about tissue products and the sustainability issue that we might have with those products, and also the topic that I always talk, and is my topic, oxygen lignification. What can we do to improve the sustainability of those processes with oxygen? And tissue products are well known for all of us. We might associate always these types of products like toilet paper, kitchen paper, napkins. There are others, and they have some specific properties that we also know, like softness. They are quite thin, flexible, they tend to have a high liquid absorption capacity, and then there are other specific properties that we can tailor-made depending on the product that we want, like wet strength or brightness. And I say brightness because nowadays we look at tissue papers like white papers, but we don't need to have white tissue products all the time. So brightness needs to be something that will change in the future, and it will turn the process more sustainable. And the problem that we have with the sustainability of these products is because, first of all, they come from trees, and if we want white papers, we also need a bleaching sequence. That is one of the parts that requires more energy and produces more effluents. And since sustainability is a greater risk for this market, is also a great opportunity to change mentalities, to change the process, and to get new products. So the market is now demanding to focus on 3 things: to change the fiber origin, to search for alternative fibers, to reduce the water consumption, and also to reduce the energy that is needed. And this presentation is more focused on the energy that you need to produce those papers. Because, as an example, and we all know how the paper is made, in the chemical process, you have the cooking, that is the first step to individualize the fibers and to remove the major part of the lignin. And then you have different steps. One of the steps that you can have is oxygen lignification. That is the main topic of this presentation. And if you want to have these really white products, you also need a bleaching sequence that requires a lot of chemicals and a lot of steps. Then you have the making part. And what I intend to show you in this presentation is that we can change and increase the sustainability of this process by eliminating completely the bleaching sequence. We can even reduce the craft cooking to a higher lignin contents, start the oxygen lignification in a higher level, and go directly to the tissue paper part. But of course, we need to compromise something, and in this case, you will have brown papers instead of white papers. And the thing is, what if white is a little overrated and brown can be really the new future? So, as I mentioned, oxygen lignification is an oxidation process that increases the carboxylic acid groups in the fibers. These carboxylic acid groups are also known as total fiber charge. So the more we increase this total fiber charge, the more we can change the properties of the products. We can increase the strength, we can increase the swelling, and we can even reduce the refining that is needed to achieve the same strength in the product. And let me try to explain you how, more or less, how this works, because we have fiber charges already in the native wood. What happens is when we do craft cooking, as you can see in the graph, you have here the total fiber charge and the kappa number, that is the lignin content that you have in the fibers. The more that you are removing the lignin, the more you are decreasing the total fiber charge. And the point here is to increase the fiber charges. So if instead we stop the craft cooking in a higher lignin content, you can see in the graph that you also stop in a higher total fiber charge level. And then if we, for the same target kappa number, we introduce oxygen lignification, what will happen is that we will increase these fiber charges. And we want this increase. We want to increase the most that we can in order to have a higher strength and a higher swelling capacity. And as the title of my presentation says, brown can be the new green because oxygen is also a greener alternative. And if we can eliminate completely the bleaching sequence, it will increase much more the sustainability. We can also reduce the energy needed by reducing the craft cooking that is performed nowadays, and we can lower the refining that is needed to the same strength levels. So the question is, can oxygen unbleached fibers replace the fully bleached fibers that we have nowadays with the same or similar properties? So the methodology that was performed in this project was quite simple. We used softwood chips, a mixture of pine and spruce. We did 2 craft cookings to 2 different kappa levels, so lignin content. One to a very high lignin content, 109, and the other one to kappa number of 61. Then we performed extended oxygen lignification in a single and a double stage. And then we compared this with a fully bleached pulp, commercial one, used for tissue. We did everything the same in order to evaluate the properties in the end. We did PFI refining because this was done in a laboratory scale, and then we evaluated different properties. And the results, starting by the most important thing to control, was the total fiber charge. This graph is quite similar to what I showed before, but with real results. So the standard behavior is pretty much this one that you see here. So the total fiber charge decreases with the removal of the lignin. But when we do the craft cooking to a higher level, like this, for example, and then perform oxygen lignification, you can see that we increase the fiber charges quite a lot when compared to the same level of lignin, for example. Then we perform the other craft cooking to a lower kappa number, where we also did oxygen, and you can also see the increase in fiber charges. So we always have a very high increase in the charges with oxygen. And from these trials, we choose 4, the ones with the highest charge. And to be easier in the following results, I will separate the results like the ones that started with the highest kappa number, from 109 from the cooking, and the others that started with the 61, so the lower kappa number. Starting with the swelling and drainage properties, you can see in this graph here, as it was shown before, you increase the water retention value a lot when you increase the charges. The reference pulp is here with almost no lignin. Those are the kappa numbers of the samples, and those are the total fiber charge. And it's clear that for unbleached fibers with high charge, you increase this water retention value. And that was the main point to do this project, to evaluate how they can behave in tissue. This is the Schoper-Riegler degree that at the first sight, it might seem not so good because we are increasing the drainage resistance quite a lot. However, I promise that I will show you later on that for the same Schoper-Riegler degree, you will achieve a higher strength. So this means that you don't need to refine so much the pulp in order to get the same strength. So you are also saving energy. Then the absorption and the capillarity properties were evaluated. We started with a basket test, that is basically to see how much water the sample can hold after dripping 1 minute. And it was quite interesting because we realized that the samples that started with the lowest kappa number have pretty much similar results in the absorption capacity, even with a higher bulk, which is very good for the tissue market. However, the samples that started with the highest kappa number, they presented worse results. Those are non-refined pulps, and here we have the refined pulps. So when you do refining, they all seem to be more close to each other, but the most important thing is when you don't refine the pulp, you can have similar properties, because we were looking for at least similar properties, not best properties, but similar ones. And you can achieve that even with a higher bulk. Then with the Clem capillary RAIZ tester, you see how further the water can go in the paper strip. And in this case, the conclusions were quite similar. So with the lowest kappa number, you also have similar results compared to the commercial fully bleached pulp. And the highest kappa number had the worst results. When you perform refining, this becomes a little bit more clear that the highest kappa number don't have so great capillarity properties. And here you have the Clem with absorption capacity, that again, the important thing is to see that we have at least 2 samples that can have similar results. We also saw in the Clem test that you have a faster and higher capillarity rate. In this graph here, you see that it's faster. And in this picture here, I'm not sure that is really clear, but you have a higher spreading of the water in the paper network that can also be very interesting for those products. Then we also evaluated the strength of the papers. And here, we have here the commercial fully bleached pulp, but we couldn't measure for non-refined levels because we didn't use additives in this case. So those are refined pulps. And those are the unbleached pulps with non-refined. So you can see that we have similar wet tensile strength with much higher bulk, which is very needed in this type of market. When you perform refining, it's clear that you are increasing the wet tensile index, and in this case, the ones with the best results were the ones that started in the highest lignin content. It's also clear in this graph here that you have an increase in the wet tensile strength when you are increasing the total fiber charge and the lignin content of the fibers, while in the other properties, the best ones were the ones with lower lignin. And like I promised in the beginning, this is the graph that shows for the same Schoper-Riegler degree, you have a higher relative wet strength. So there is no need to refine so much the pulp, or you can also even don't refine the pulp, as I showed in the other results. And here again is the relation with the total fiber charge and the relative wet strength that we can have. So as conclusion, we can separate this in 2 parts. If we are looking for absorption properties for these tissue products, unbleached tissue products, we might need to research more in lower levels of lignin. We saw that we have a similar absorption capacity, a higher spreading, and a higher capillarity rate. If you are looking for a good wet tensile index without using any types of additives and don't have bleached products, you might need to start in a higher kappa level where you have the highest total fiber charge and the highest water retention value. And this, of course, is just the beginning of a lot of studies that needs to be done and to be a little bit studied further. The fiber charge is important, but is not the only factor that can determine or be determined for those types of properties. And this is quite a complex issue that needs to have more trials and more results in order to have clear direction of the future. But we can improve the sustainability of the tissue products by starting by changing mentalities, that we don't need white products, and by changing a little bit of the process itself. And thank you very much for your attention.
Thank you very much, Cláudia. Very interesting presentation. And now we have a time for questions. I'm sure that there will be a lot of questions from the audience. It's still early in the morning, but both teams were very interesting, so I see a lot of people here. We have there, please.
Is it good? Yeah. So good morning, everybody. Thanks for nice presentations. And thanks for starting the morning like this, because this last presentation from Cláudia, and that's my question, is actually not a presentation, but actually an act of revolution. Because the title should not be brown is the new green, but probably brown is the new white. And so that people understand the implications of that, and coming from Altri, from a pulp producing group. So the main application for market pulp, and not integrated pulp, but market pulp, is actually tissue. So what we're actually hearing here is that probably bleaching is not necessary anymore for pulp producers. So that might mean all the bleaching lines that's out there for the market pulp producers are obsolete. So my question is more of a reflection. Do you believe that this trend will continue in the future? And if so, the pulp producers will need to adapt, and how? And if you see that if this trend is actually more than the tissue itself, can be a trend that will be applicable to all other paper segments, meaning that if you don't need white, then what else?
Thank you for the question. I think the point is we always will need bleaching for some specific reasons. And of course, comparing fully bleached pulps with unbleached pulps, you don't have exactly the same properties. And some products need those specific properties like high softness level and things like that. What I intended to show with this presentation is that we need to change our way to look at the products, and so many times we use tissue products and they don't really need to be white or soft. They just need to absorb liquids or other types of things. And we can change the sustainability quite a lot, not to remove for always like the bleaching, but to remove for some products and to at least save some energy in the products that we don't need to have white papers. And I think the industries needs to change more through this sustainable view of brown products, because all the legislations that are going on now, it requires that you reduce quite a lot the emissions, the energy used, so you need to adapt and you need to change something, otherwise you will not get what they are imposing. The other part of the question was... Yeah, we can also use this approach or see these benefits that I showed in this presentation for other types of products, like packaging products. Everything that is brown already has a lot of potential with oxygen lignification, because you are increasing a lot the strength of the paper without the need to use any types of additives or any types of processes that requires more energy. Even with the refining, you don't need to refine so much. So I think this is something that can be applied to different markets. And it depends always what do you want in the end. So it can be tailor-made. Thank you.
We have another question.
Yes, thank you for the presentations for both, and especially for the wastewater treatment presentation. My name is Heikki Hannukainen. I work with wastewater treatment plants in Finland. It's a really personal thing for me. I've been working with more than 40 mills in general, and you showed results about nitrogen and COD ratio, and I took some notes. Maybe you have the results we didn't see, but did you consider when you change slash H that you also change parameters like flock load, circulation number, sludge load, which have really big effect on the flock formation? And also phosphorus, we need oxygen, phosphorus, nitrogen. I saw that you are improving with nitrogen, but did you consider these other parameters that have big impact on the flock formation?
In our industry in Portugal, we have a lot of phosphorus, so it's not a problem. And oxygen really depends on the design of the installation and the capacity of aeration, and varies accordingly to the COD that it's coming to the wastewater treatment. So we focused in the sludge H and in the nitrogen. And that's it, and really goes well, so.
Any more questions? Get one back there. Lá atrás, lá atrás.
For Cláudia Esteves, what influence of the hemicellulose in the total fiber charge and in water absorption and tensile properties of the tissue paper?
I'm sorry, can you repeat the question?
My question is if there was any influence of the hemicelluloses in the total fiber charge and in tensile properties and water absorption of the tissue paper.
You asked if we had any losses in the hemicelluloses?
Because if hemicellulose also contribute to total fiber charge, how was this evaluated?
Yeah. In this case, we didn't evaluate the carbo composition of the pulps, but I evaluated during my PhD research. And there is no losses, significantly losses for the hemicelluloses. And the carbo analysis of the pulp is quite similar when you compare to a just craft cooked pulp, for example. And I think you also asked about the tensile properties and the water absorption value, right?
Yes.
Yeah. They are always higher for the oxygen unbleached fibers when you increase the fiber charges to a certain level. You don't. You need to do the oxygen lignification in an extended way in order to have these better properties. If you don't do that, you will have the same or worse properties. So maybe I didn't mention so much here, but the trick is to do extended oxygen lignification in order to achieve the highest oxidation possible to increase the charges. And that is what will give you the good properties. I hope I answered your question.
Yes.
I cannot hear you, I'm sorry.
You would
Yeah, I assume you asked about soft and hardwood. We only did the research in softwood, but in the future I really would like to do it with hardwood to see the differences, because there might need to be differences. Thank you.
I think you still have some time for some final questions, if there are. If not, I have to earn my earnings here, so I have one question for each the presenters. From the presentation about tissue, technically we know the stuff, we study the stuff, we have the solutions. What about the market? Do we have any idea about the market will receive this type of products?
Thank you for the question. Yeah, I think that this is the main issue, the market, because when we talk about brown pulp, they usually don't receive so well that part, and they have very high standards of brightness. But the thing is, we need to change mentalities and the processes in the future. There is a need. It's not something that you can choose in the future. You will need to change something. So if you can have at least similar properties, I think to be brown is not so bad after all, and they need to. And we already have the products in the market now. We already have napkins that are brown and some other types of products. So I think it's a process, and it will change, and it will be brown in the future.
So just thank you. Just a final question to get. There's another one there. Sorry. Yeah, maybe it's better because here it's hard to hear.
So, thank you so much for both communication. They were really, really interesting. It catch me up until the end. Thank you. Just one question related to the brown, the midway to you, Cláudia, please. This is really interesting, and we know that we need to change mentalities in society. But we have an idea of what will be the cost for final consumer, because this, at least at this moment, and in any moment, this will impact how people will choose white or brown, because if the cost is higher, it will be difficult, but if it's lower, I think people will really addict.
Thank you for the question. And that's the good part, because the cost should be lower, because you are saving energy in basically all the process. You are first removing the bleaching, that is a big part of the cost. Then you can also reduce the craft cooking, so you don't need so much energy to produce the same pulp. Then the processes are more or less already implemented in most of the mills. And you also don't need so much energy to refine the pulp if you need to refine. So it's always saving energy, and there is not so big cost associated with this change in the process. Only if the companies, the industries need to change and to buy new equipment. That is a new cost, but in the end, it's saving all the time, I would say. So the product shouldn't be more expensive. And I think nowadays the consumers are choosing more for sustainable products, and I think we all associate sustainability with recycled papers or brown papers. So there might be a tendency for consumers to start buying more the sustainable ones, like the brown ones, than the white ones. I would choose that, so thank you.
Okay, so we're getting to the end of this session. I'll just make my combined question to Catarina. But you showed us that increasing the ratio between nitrogen and COD improves a lot of stuff. But of course, nitrogen is also a parameter that we have to control in the final effluent. So are we taking any risks on this?
You think yes, but with the optimization, no, because I showed you that the sedimentability improves, and with the improvement of the sedimentability of the sludge, the solids in the end, in the final effluent, the solids that come to the final effluent are reduced, and so the nitrogen that would come with the solids reduces. And if we increase the ratio of nitrogen COD, we are increasing also the COD removal. So the only thing that we could risk it's when we have a peak of something that it's not so biodegradable that comes to the WWTP. We have to check and reduce or stop the dosage of nitrogen, so that we don't have a higher value in the end. But with optimization, it still works. And thank you.
Okay, thank you very much, everyone. We'll end this session. The next session will be on pulp production, and the chairman will be João Martins, that will be leading this next section. Thank you very much. Have a nice day and nice congress here in Coimbra.